Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
All right, welcome everybody to the AI for Good webinar today. I am glad to welcome Dr. David John Garnier. He's a machine learning scientist and head of the Machine Integration and Learning for Earth Systems group at the NSF National Center for Atmospheric Research, NCAR, in Boulder, Colorado, USA. He received his PhD in meteorology from the University of Oklahoma in 2016 and completed an NCAR postdoctoral fellowship. He has led the development of machine learning systems that enhance our understanding and prediction of high-impact weather and critical Earth system processes, including NCAR's Credit AI Earth System Prediction Research Platform. He co-leads the WMO AI for Nowcasting pilot project and is advising organizations on the future directions of AI for Earth system science. Today, he will talk about incorporating scalable physics and uncertainty into AI weather prediction. I'm very much looking forward to your talk. David, please go ahead.
All right, thank you, Alex. Let me go ahead and pull up the slides here. All right, hello everyone. Today I'm going to be talking about incorporating scalable physics and uncertainty into AI weather prediction, both as a broad overview and then kind of a deeper dive into the work we've been doing at the US NSF National Center for Atmospheric Research, kind of in this area and where we think things are going with this new class of exciting models. So we'll start off, what is the value of AI Earth system prediction? Kind of from a global perspective, for most of our modern era, weather modeling has been dominated by a few government weather agencies, such as the US National Weather Service, the UK Met Office, ECNWF, and other countries with their own modeling suites. And these all have basically large supercomputers, require lots of data, lots of staff to develop these systems and maintain them. Over this time, there's also been the development of both statistical and AI and machine learning methods that have provided usually corrections or derived products to our physics-based weather prediction models. So things like model output statistics or other post-processing methods. However, in the last 5 years, we've seen a lot of advances in data sets, like the release of the Era 5 reanalysis, a series of more increasingly complex machine learning models, starting with kind of initial deep learning approaches, but growing to our modern transformers and other more advanced architectures, as well as advances in GPUs to the point where you can fit the entire state of the atmosphere inside the memory of one GPU. This has all sparked a new revolution in building to fully AI weather prediction. And we've seen this just over the past 5 years. We've gone from kind of initial tests of 500 millibar fields to predicting full states of the atmosphere with greater global accuracy than the ECNWF IFS deterministic run. And now we're getting the first ensemble AI models, and all these are kind of moving to operations already. So it's been a very fast transition, especially for the field of weather prediction, which tends to operate on a much slower timescale. So what are the values of these AI weather prediction systems? One of the big values is, as I mentioned, the major jump in prediction accuracy. This is a figure from a paper by Bauer et al. That came out recently, kind of showcasing the IFS, the European Center for Medium Range Weather Forecasting's global physics-based model. It shows slow but steady growth over the past 2 decades. But then once you get to the release of the AIFS, we see a jump in accuracy just from this new model that by some measures it may be like 5 to 10 years of work on a traditional model to get the same kind of jump in accuracy. The other big benefit we get with these is, at least on the inference side, so actually running the predictions, we can get a huge reduction in computing for generating simulations. So at NCAR, we have the community atmosphere model, which is our atmospheric portion of our system model. To do a prediction at 1 degree resolution over the globe, it takes our supercomputer with 10 nodes takes about 14 simulated years per day, versus our cumulator model trained on the same data. We can run this and produce 480 simulated years per day of climate projections on 1 GPU. So when you're talking hundreds of orders of magnitude speed of hundreds to, depending on how you organize the model, thousands of times speed up on the inference side, there is a lot to be gained, and it opens up a whole lot of new possibilities in terms of how you could actually deploy these models, what kinds of questions you can ask, and how you can use these in a way that you couldn't use a traditional global numerical weather prediction or climate model. However, even with this promise, we're still seeing some issues before we go all in on AI weather prediction and going out to longer timescales. And one of the bigger issues is while the accuracy is really good, the physical consistency is sometimes leaving things to be desired. So we have an example from a paper by Charlton Perez et al. This showcases an extratropical cyclone off of the coast of Europe. And we can see kind of major weather features, such as the warm conveyor belt of moisture feeding into the storm, basically the cold front, kind of an occluding extratropical cyclone, and we can look at these features. So this is in kind of the reanalysis or best guess of what happened, the high-res ECNWF model, and then other top-line first-generation AI NWP models. A lot of them have the broader scale features, but they're missing, they're underdoing the strength of the cold front and the gradients. They are missing, some of them are missing things like the kind of occluding low that's wrapping around. Some of them kind of get it, but they're still kind of underdone. And some of the winds are also not as strong and not as concentrated as they could be. And so that means they're not fully capturing all the physics we expect one of these kinds of models to capture. So then the question is, how can we change that? So one way is to combine the best of AI weather prediction with physical constraints of various sorts, and seeing how we can make a better model that way. So there's a number of groups that have already been digging into this. One, the Google's Neural GCM, which takes a traditional dynamical core, but written in Google's JAX domain-specific language for basically GPU and TPU portability, as well as auto differentiation, plus a neural network physics. There's a model called ClimODE that decomposes the prediction into NeuroODs for part of it, for different components, so advection, emissions, and local and global state updates. The Aurora model from Microsoft has physics-informed state embedding that kind of goes into the model, and that helps it be a little bit more physics consistent. But also things you can do not just on the architecture, but also on the data end. So one innovation is the HELPix grid from the astronomy community, but adapted into the weather community, that regrids the Earth into equal area cells at a consistent directionality. And that means the model has less to learn as it's making its predictions, so you can use a less complex architecture to get similarly good results. But then some of these require a lot more intervention into the model than others. So one of the things we wanted to explore with our group is what if there are ways to add physical constraints that are more architecture agnostic, so that it doesn't matter as much what the architecture is, but you can still impose those constraints during both training and inference to make for overall better predictions. And so the goal for this part of the talk is we're going to analyze data and post-model constraints for how they can improve the overall performance and the physical structures of our weather predictions. So we're doing this within the framework my group developed, the Community Researchers Digital Intelligence Twin. The idea behind this is we wanted to develop an open foundational research platform for developing AI Earth system models. Part of this is there's a number of other competing platforms out there. Some of them are more operationally focused, like US NWP platform. And that is great, but sometimes it may be hard to experiment with the whole data pipeline if you're dependent on one particular modeling center's sources of data and how they process that data. And so we wanted to build our platform to be very flexible and modular in terms of what data sets you can plug in, what kind of models you can use, how you can incorporate physics, and then also how you can incorporate different kinds of pre and post processing. And so we built this into a full pipeline, and we're continuing to openly develop this to allow anyone to train customizable AI models at scale and then deploy them for forecasting and hindcasting or making projections out far into the future. We're also continuing to openly develop this. It's all open source. We're working on new releases as we speak. And we're building a user community and collaborators to work with us. So we're open to other ideas. And as a research platform, it's not meant to be like kind of constrained to one approach or another. The flexibility is intentional, and we hope that by having more people use this, they can experiment beyond just like trying a new architecture on an existing benchmark, but really thinking through the whole pipeline and being really creative and using that creativity to inform more operational platforms that are out there. So in terms of our physics constraints, this is all based out of a paper that came out this past year in James. So you're welcome to go look up the paper if you're interested. The idea behind this is first we take a set of variables. This is using Error 5. And what we wanted to do was add in some additional variables that allow us to calculate some of the physical constraints that are important on the problem. So things like heat fluxes and other surface features. And that will allow us to calculate both a dry air mass budget so that we can conserve dry air mass globally, a moisture budget so we can conserve our moisture budget globally. And that includes predicting things like not just precipitation, but also evaporation. And then also conserving total atmospheric energy. And the way we do this is we make the predictions from our model. We use the Fushi model architecture for this. And then we apply what we call post blocks. So these are architecture agnostic. You stick them on the end of the model. They know what data is going through them. And if you apply them in the right order, you can then basically conserve your dry air mass. And then assuming your dry air mass is conserved, you adjust your moisture budget, and then you adjust your total atmospheric energy. And we do this by basically doing a multiplicative perturbation on some of the fields that are related to dry air mass or moisture or energy. Then we do this during both training and inference, and this basically helps the model basically stay on track, stay in the right manifold or part of the space that produces physically consistent solutions, while still minimizing prediction error. So finding that balance between the two. So the question is, how well does this work, and does this actually give us better forecasts? So first, we want to validate that we actually are conserving mass and energy. One of the challenges we ran into is that Error 5 itself does not actually conserve mass and energy. It kind of varies throughout the year. You can kind of see this in our both original Error 5, and then we also coarse grain this to 1 degree to make it easier to train the model. We see the same pattern when you do the coarse graining. But then from there, we can then apply our mass constraints. And when we look at dry air mass, we see that without the constraint, we get a lot of variation over the course of a given run. Basically, this is our baseline model, same architecture, same variables, just no physics constraints. Versus with the physics constraints, we get nearly constant conservation. It's not perfect because there's still some 32-bit floating point precision issues, but we're not seeing any drift with this approach. And we see the same behavior with global moisture budget. There's a lot of variation over the course of the year. We constrain it. We don't see that variation. And we also see improvements in both our predictions of total precipitation amount and global evaporation amount. versus the baseline model, which tends to drift the further out you go in time. Then we also tested this doing a full year-long run. So both models are able to run out a full year without completely blowing up. We do get some wave-like artifacts in the baseline model, but we are able to preserve overall behavior. And I'll say how we also, if Verify doesn't conserve physics, how are we actually preserving this? We take whatever the values are at the initial time of the run, and we conserve that over the course of the run. So if you're wondering, yeah, so if you started here, you would get a different conserved value than if you started here. And then yeah, we can basically see things behave as they should. So how does this translate into improved forecast skill? It actually does after some period. So once we get to about 96 hours, so about almost between day 4 and day 5, or I guess about day 4, we do see we start to see the two models diverge, and our baseline model starts doing worse than our physics constraint model. And this is true for the baseline and for like temperature, geopotential height, mean sea level pressure, a lot of other state variables. Some of the differences are they're not equally globally. We see some of the greater improvements kind of in the mid latitudes and near the poles, and that tends to be where some of the bigger artifacts tend to show up. So that's also good to see. We also did some ablation testing. So one of the big ones and questions we've gotten a lot is, why not just apply these constraints during inference? Why do you need to apply them during training? And it turns out that if you apply them only during inference, you can actually get a much worse prediction than you would if you just let your baseline model run. It's because it's pushing the model way far away from what it's used to if you've been training without constraints at all. But with constraints, you can, even with small constraints, you can see slight improvements in prediction. So if you just use mass conservation, you get slight improvement, and mass plus energy get even more improvement. But with turning on the only inference, it gets a lot worse. The other variable we actually also see improvements in is precipitation. So this is one of the ways we actually see improvements is not in terms of getting extremes better, but we get rid of a lot of what's called drizzle bias. So sometimes these models will produce very light precip everywhere, and this accumulates over time. It can cause problems in like land state and in the overall fields and how they respond. So with the physics, if you look over, like say the Sahara or the Kalahari Desert or in Antarctica, you can see compared with the baseline, the IFS does a pretty good job, but even in Antarctica, it sometimes has some precip. But with our correction of drizzle bias, we basically get barely any precip in these areas, also preserving extremes across the globe. And this translates into better predictions as we go over a 1-year model forecast. And this one, if you look at the difference between the baseline and the physics model, you actually can see some of the artifacts that kind of show up in the data, especially near the poles. And so we are like, it's helping the model be more stable and produce better results. We also even see this in storm structures. So this is a example case for an extratropical cyclone over Europe, similar to the one I showed earlier in the presentation. And this one we can see, like if you look at 500 millibar geopotential height and temperature, here's our Verify baseline. The IFS actually does not have as nearly as strong a temperature gradient or as strong a low. This is just not a great case for this particular model on a day 7 forecast. Whereas with our AI models, they tend to lock in better. But the baseline physics model, it doesn't get the structure right, whereas it's a little bit better at the gradient, but not the right structure. Versus the physics constrained model, we get better structure, both on the horizontal, stronger temperature gradient, more correct placement at the low. And then in the vertical, we also get a stronger potential energy to kinetic energy conversion. This is much better represented in the physics-based model and much more aligned with Verify compared with both the IFS and the baseline model. We've also tested, so not just adding physics constraints to a model using pressure levels, but I also wanted to see the effect of changing the vertical coordinate system. So a lot of weather prediction models tend to use what's called a hybrid sigma pressure vertical coordinate system, also known as terrain following coordinates. And the reason they do this is because if you use pressure levels are smoother in a lot of the mathematical equations for weather prediction work really nicely along them, pressure levels tend to run into terrain near the surface. And so finding a balance between the two can allow you to account for terrain variations without like some of these terrain variations, however, can induce spurious waves and other things that don't look spatially as smooth. So it's an inherent trade-off in the model that you have to make. But we wanted to test combining these physics constraints with this vertical coordinate system to see, does this give us further improvements, especially near the surface? And we focused on precipitation for this. In terms of our large scale scores, we don't see, I would say we don't see a huge difference in performance improvements. We do see some in the physics constraints themselves have the biggest help. Switching from the vertical coordinate doesn't make as much of a difference, but combining the two does give us some improvements, especially we see at earlier lead times, and then things kind of blend together once you get past day 6. But both of them provide a big improvement over our baseline models, both with either vertical coordinate system. We also see this in more directly in case studies. So sometimes the global metrics don't always capture the fact that like a given system may like the kind of intensities for very small areas. And what we can see with our IFS versus, and these are day 5 forecasts. We see both better precip and better wind representations with when you combine the physics, like just having a better vertical coordinate system gives you better representation of low level winds and kind of how they're affected in interacting with terrain. With the pressure level models, we see some improvements with the physics constraints in terms of the wind structure, but without them, it really underestimates precip. We also can see this with a kind of a more of an atmospheric river style event over British Columbia and Canada. Same kind of pattern where we get stronger winds that are more in line with what was observed, and stronger orographic precip over the mountains that is present with the sigma coordinate system, less so with the pressure level data. So these physical choices do have an effect. It may not show up as much in the global metrics, but in individual cases where it can matter, you can definitely see some differences. So that's kind of physics constrained ensembles can help, but the kind of another piece of the puzzle is uncertainty. With a lot of high impact weather events, in the lead up to them, there can be a lot of uncertainty, and where is the placement of the low and the highs and other blocking patterns. And so ensemble prediction has become a mainstay in a lot of global numeric weather prediction suites. The problem we run into with these systems, though, is that because of the computational expense of running even just a single high-res numeric weather prediction model, usually ensemble sizes tend to be fairly limited to order 30 to 50 members, which characterizes kind of mean behavior. Okay, you can get some performance improvements, but when you're talking about extreme events, especially things that really on the tail of the distribution, it's really hard. Like it becomes harder and harder to characterize those. You can't really characterize them with a small ensemble. You really need large ensemble sizes or more targeted ensemble perturbations to sample that tail. The other challenge you run into with, even if you have a large ensemble, is how do you actually analyze it in a reasonable amount of time? So in some cases, you may need more curated interactive analysis tools to do this. Google had an interesting ensemble interface they debuted this past hurricane season, and were able to showcase kind of greater spread and their larger ensemble that indicated potential impacts to Jamaica for this storm, Hurricane Melissa, well before the physics-based models were hinting at that as the main course. Even multiple days out, it's still the most likely outcome was still going through Hispaniola, but that did have numbers indicating the potential for a more intense event. So the question is, how do you actually train one of these models? a lot of groups have been, a number of groups have already developed these ensemble approaches for AI NWP models, and they do this by optimizing on a loss function called the continuous rank probability score, CRPS, which is a well-behaved ensemble loss. And this actually works pretty well. But a lot of these groups are currently providing one perturbation inside the middle of the model and then training different models from scratch to get lots of ensemble variance. Challenges, this requires more GPUs, which not everyone has easy access to. So what if we could come up with a way that could give a similar skill to these like trained from scratch models, and also allows us to perturb at different scales in the model, so we can actually have some interpretability in how we're perturbing the model. And so we can do this with fairly minimal resources, like you could potentially do this on 1 to 4 GPUs rather than on like 32 to 64 or 128 GPUs. And so we developed a new technique. So we take our Wex former architecture that we developed, and we inject noise into these learned noise blocks that combine basically take just a normal random noise vector, and then injects a modulation parameter that we learn through kind of fine tuning while freezing the rest of the weights of the model. And then we inject additional pixel level noise on top of that and combine them all together. And that gives us perturbations to the fields. You could we're currently doing the perturbations globally, but you could also do local perturbations if you're interested in kind of local sensitivities. And you tune this, and the result is we get a well-calibrated ensemble. So for comparison, our baseline members are comparable with the IFS HRES. So we're about equal on Z500. We're a bit better on some of the surface fields, especially on 850 moisture and temperature and winds to some extent. And then we see our CRPS, we get improvements over the IFS ensemble pretty dramatically, especially on 850 moisture and temperature. And we see our spread skill ratio is pretty flat near 1, which is good, which is what we're looking for. And we're even a little bit better calibrated at earlier lead times compared with the IFS ensemble. We also can look at these rank histograms, and basically, ideally, these lines should be flat. If they're bumped up like this, that means it's a little bit over-dispersive. So at shorter lead times, it tends to be a little over-dispersive. At longer lead times, they tend to be well-calibrated, a teeny bit under-dispersive. But we're seeing comparable skill to other models that are doing this, but with a lot less fine-tuning required. And then one of the cool things we can also do with this is because we have a scale-dependent way to perturb the model, we can then perturb those and look at how it affects our kinetic energy spectra. So if we perturb at our synoptic scale, we see more variation in the synoptic realm, versus at the meso-alpha scale, we see a little less energy at the really high scales and sometimes less to more energy at the finer scales. And then if you perturb at the finest scales, you see more variation only kind of at the finest weighted number, so this part of the distribution. And so this gives us some knobs we can now tune and have some impacts on the model state in addition to kind of random perturbations. We can also up or lower the amplitude of the noise. And when we do this, we seem to get some like spatially specific perturbations. So it doesn't equally perturb the globe everywhere. We actually get perturbations more near the poles and near the mid-latitudes and less near the tropics, which is what we were kind of hoping for. And it's kind of where more of the variation is happening. We see that's where more of the perturbations are also happening. So it kind of the perturbations are physically structured and realistic, and they also kind of occupy different scales, with most of the energy being in the kind of this middle one. Another cool thing you can do with this is if you have perturbations in the latent space and you have a latent structure you can mess with, you can take two members and take their latent representations and then do a smooth, like interpolate linearly in that latent space between them and still produce physically realistic intermediate states that can allow you to launch additional ensemble members from the ones you have already perturbed. This can allow you to explore sensitivities between, say one event has a really strong low and the other one has maybe a slightly weaker low or in a different location. What else is different about those situations? And that can provide some level of ability to analyze sensitivities and look for precursors that could be major points of like an event that could turn from a really high impact event to something of a bust. we're also looking at a lot of, I'd say, ongoing challenges in the space. So the ensemble work is very promising, but it's still kind of in its early stages. With this, there's more broadly in AI NWP, there's still a lot of ongoing challenges that we're working through. One is that the AI NWP is only as fast as the slowest part of the process. And one of those processes is training, but the other one is dependence on physics-based models for initial conditions, as well as on our whole analysis suite, kind of going through well, right now we can run our model really fast on the GPU, but then the slowest part is actually interpolating from model levels to pressure levels. That takes much more time than it takes to calculate the whole state of the atmosphere. That seems like a sort of a problem. How can we should be able to fix that? So starting with the data assimilation problem, right now our data assimilation systems require a physics-based model to learn the relationships among variables, the covariances between different fields. There have been some tests to put in AI NWP models to use as that source of those relationships among different variables. The problem is that these models don't learn those relationships perfectly. That's going to bias the data assimilation process and make for a worse analysis than if you use the physics-based model in the first place. So that's where these physics constraints are really important, and making sure we actually learn these relationships properly, and more heavily emphasizing that both in how we architect the models and what kind of constraints we put on the loss and on the output of the state. And we think that that newer architectures and training, like of what we've shown, and then other things that build upon this could help address some of these issues. We might even be able to there's also groups working on purely observation-driven NWP models, or AI NWP models, where they try to learn directly from observations and make that predict forward in time. I think that's also promising, but without physics constraints, because this problem is inherently underdetermined, we don't have enough observations everywhere. I think that's going to, without some way to do some kind of assimilation and analysis and updating of priors, I don't think that's going to work super well until we can find that right combination of everything. But if we can make this work, then that speeds up the whole process. We can do cycle data assimilation with AI systems and even build new data sets out of that. So there's a lot of interesting possibilities in that space that looking forward to seeing more progress in that area. So the other big one is the shifting existing data bottlenecks and creating new ones. So if you can, the point of this is if you generate a huge ensemble, like let's say 1,000 members or 5,000 members, this is going to require a lot more I/O and data storage if you actually want to save out everything, or you're going to have to do more selective saving of fields and combinations of things in memory, whether it be store and tracking or other kind of feature-based things or aggregation. And this will require re-architecting these systems to handle this kind of large distributed data transfers. So then we're kind of back in the high compute end of the regime, which can be limiting in its own ways. That said, most of these samples we're interested in may not be the ones that are sampled by the bulk of the distribution. We're often interested in the tails. And so there's a recent paper, Lancelin et al., AI boosted rare event sampling to characterize extreme weather, that actually looked at this problem from can we use an AI emulator to steer models toward higher impact events? You let it basically run forward and see, does it actually give us a high-end heat wave or some other kind or major tropical cyclone or something like that. And then you kind of nudge the numerical model, what samples you use, you kind of favorably sample the ones that are more likely to produce a high-end event. And because you still have the full ensemble, you can then still have a somewhat calibrated distribution that comes out of this, and sample the tails more effectively than you would with a smaller ensemble. And so this is an interesting hybrid combination of the two, and I think there's more interesting work to be done kind of in this space that allows us to potentially avoid the headaches of the huge ensembles, but still get the benefits of looking more into the tails. So where are we going in 2026 with credit? We're interested in a lot of these things. tackling these challenges I just brought up. We'll have a new release of our code. You can go ahead and download it now. It's already available, but we're planning a new official release with our some new feature upgrades and bug fixes coming next week at the AMS annual meeting. And we also have a regional model that we've been working on, led by Kyle Shaw. This is trained on CONUS 404 and features basically 4-kilometer output that's forced by either it's trained on error 5 as the forcing, but you can plug in GDAS or you can plug in an Earth system model as the forcing and do downscaling for both in current climate and in future climate, and it seems to work well in both. And we're getting really realistic state fields, especially it captures terrain and winds and temperatures really well. Precip is still, I would say, a little bit more of a work in progress, but we are getting a decent signal out of it, and I think there's room for further improvement. But the first go at this is looking really promising, and we're going to be showcasing that. Kyle will be giving a presentation at AMS next week, so if you're going there, stay tuned, and otherwise look on the archive once the paper comes out. We also are planning a lot of different platform upgrades. We're working on simplifying our data sets and adding new what we call pre-blocks. So I talked about the post blocks for physics constraints. We also want to do pre-blocks for data transforms to make it easier to learn on some of the fields that are a little less Gaussian, like moisture fields and others. We also built a lot of infrastructure for interpolation diagnostics, and some of that is in CPU-based Python code, and we want to move it all to PyTorch so that you can run the whole thing through in one go and get a very powerful, fast state in whatever grid and vertical levels you want. We're also working on streamlining our training and inference. We're getting more software engineering support, and a lot of what they're working on is going to be making the interface easier to use, even more modular, even more accessible to users who don't have a strong machine learning background. And we're also interested in rare event sampling, as I just discussed, and we're looking at some different techniques for that. Some other new models in development. We have a satellite nowcasting model that's trained with our WexFormer architecture that we're seeing some promising initial results that we'll showcase more in the near future. We're in the process of building up our data set, kind of going for WexFormer generation 2 at 1/4 degree. A lot of our experiments are shown here at 1 degree. We're based off of what we've done with this. We want to build a new model that has all of these bells and whistles at the full resolution, so that we can use that as a flagship model for a lot of other applications. We're also working on an ocean emulator. We're working with some of the members of the Samudra team, as well as kind of trying different architectures and looking at both global and regional opportunities in the space. And we're also playing around with new losses and vertical representations to see how we represent the structure of the data, and how we can optimize on it can help us address some of the issues we're seeing with, say, poor performance in the stratosphere, or how can we reduce the memory footprint and make these models more effective. So there's a lot of exciting directions, and we're also open to other collaborators who want to try anything else with this platform. It's still a work in progress. We have a core community of users that are doing cool things, but also finding issues, and we're welcoming more folks to try it out and let us know how we can make it more useful for them. So in summary, I think we're at a stage with AI weather prediction where we've proven out that this really does work well, but that there's some key issues that I don't think are going to be solved purely with adding more data or fancy architecture. It's something where we really need to think about the physics during both training and inference, and incorporating that with good ensemble perturbations that can allow us to explore sensitivities and kind of the whole range of low and high impact events. And there's ways to build these ensembles cheaply, so it doesn't necessarily require all the giant computing in the world to do this. With that, I wanted to thank the whole credit team. They're all listed here. If you have questions, you feel free to add them during the chat, or you can email me afterwards. And our code is on GitHub, so check it out there. We have documentation and the active issue community, and feel free to reach out. With that, thank you. I'm happy to take questions.
All right, David, thank you so much for this nice overview talk. While we are waiting for the questions to come in, I would start maybe with a basic question, maybe also more on the first part that you showed, is how much of this constraining of the AI with mass balance and other physical constraints can also help maybe towards climate modeling?
It certainly helps a lot. I didn't talk about it here, but we have another model called the Camulator that's trained off of the community atmosphere model. Basically, we did a 30-year climate model run with a traditional climate model, and then trained our Wexform architecture with these physics constraints on it, on that data. And we found that it can run stably with the constraints. It runs stably out indefinitely. It can learn some of the kind of global warming temperature patterns, and we can force it with, let's say, SST and have it simulate a kind of warming climate mostly stably. There's still some issues with vertical exchange of heat but it can learn teleconnections. It can learn like a lot of other structures, even learn some of the biases of the original CAM model and how it represents the MJO. And so because it's just the atmosphere model, we're also interested in, that's why we're bringing the ocean, is we're interested in coupling the two and being able to make have a whole, eventually get to a whole Earth system model. It's still a little ways off, but I think in principle it should be doable. And there's already some groups that are already looking at coupled atmosphere and Earth system, or atmosphere and ocean models, and atmosphere and land models. So I think it's just a matter of time and effort and getting the right data together to make this possible. But yeah, the physics constraints are definitely necessary and very helpful for getting good climate predictions.
Right. So are there also plans to bring in like carbon cycle components?
I think in the longer run, we're still, if we have the right training data and variables, there's no reason, like we added CO2 as a field. One of the challenges some of these models have run into is if the data they're trained on has signal, like say both SST and CO2 are increasing at the same time, the model may not be able to distinguish between what is causing the force response, basically. So that's potentially where adding other carbon cycle components and like carbon fluxes from the atmosphere into the land. It's something you could add. It'll probably require more like land and ocean components to explicitly handle that. But it should be possible. It's just working through all the details of getting that trained well and performing well is a big effort. And this is where we still need a lot of, I say, domain scientists to actually help us validate what are the right variables to include, what are the things that are important, how should they be formulated, how should we even be evaluating these models? Because there's still a tendency just to look at the mean squared error and say, oh, look, it looks great, but then it may not be getting some of these physical processes correct. And that's where having people who actually know these different Earth system components, working with these models and looking at them, is critical to make before we deploy them and make lots of other scientific decisions based off of them. We need that level of validation to ensure what is the range of validity for what they're good at and what they are not.
Oh, all right, thank you. So I would encourage to submit questions via the chat, and while you are typing in your questions, I would maybe also ask a question more towards the future. Where do you think, now if you go maybe 10 years into the future, where do you think what will weather prediction be like? Do you think there will be any type of process-based or classical weather prediction, or do you think this is in 10 years we only have AI, or even in 5 years?
I think there's still a strong place for process-based models, and I suspect they will still be running in some capacity. Whether the amount of resources going to their development is going to be the same, it kind of depends on how the AI development continues to play out. There's a number of directions that could happen. One, it could be, I doubt we're going to just drop all these process-based models and go entirely to AI models, because they come from different sources of assumptions. The process-based models allow you to kind of have a more deductive approach to plugging in, to trying out new processes and exploring things that haven't been done. One of the weaknesses of the pure AI models is you still need a training data set from which to build the model. Something in between where you have more physics informed components or say like it could be an AI dynamical core or a physics-based dynamical core and AI or physics-based other components. I suspect we'll see more of these hybrid approaches. What I see already happening is groups are kind of trying to move their code from more traditional Fortran to either C++ or other domain-specific languages. I see that continuing to happen, and hopefully you want to see more development of more robust interfaces between these different kinds of systems so that it's easier to pull data as needed for either online training or fine-tuning for particular models, or having like good reference codes. So if you are trying to say develop an emulator of an expensive parameterization, that you have something you can compare against really effectively. I said, like my concern with going maybe too much down the AI rabbit hole is everyone's chasing the same target.
Yes.
We're going to lose a lot of innovation just from people not being creative. They're all like, I've already seen this kind of in the AI NWP space. They're like, sometimes there's like, oh, let's all do diffusion or let's all do CRPS losses, and say we're not entirely not guilty of some of that. But if we're all chasing after the same puck, there's a lot of other missing opportunities out there, and that's where I think tools like Credit, where we can do more creative exploration and enable more people to try out their ideas in this kind of framework, especially people who aren't coming from the machine learning background or aren't interested in going after the big benchmark numbers. I think that's where a lot of the cool innovations are going to come from. That will drive us either toward newer process-based models or combination of process-based and AI, or newer AI models that incorporate more physical constraints and processes.
Yeah. Thank you. That's quite insightful. So what you also mentioned, we were talking about extreme events, and that there's always sort of a problem that, covering just edges of the distribution. So maybe you could elaborate again a bit on what one could do in the development of such models to better, represent such rare events.
Yeah, I think some of the things, I don't want to say too much about what we're working on at this point, but I think there are definitely techniques out there that can help you sample rare events more effectively. There's also just how can you improve your representation of your model state. So one of the things a lot of the AI models struggle with right now is convection and vertical exchange of information. I think that's part of the reason why they underdo convection in the tropics. They don't really handle the stratosphere very well, because the stratosphere itself is more stratified, and so if you aren't handling vertical exchanges effectively, you're going to like miss some of the structure in the stratosphere. There's also like separations of timescales, so they can learn fast timescales fairly well. Slower timescales, if they're happening at the same time, the model may emphasize one over the other. So there's, I think, still a question about how best to represent a whole range of timescales. Is this something you need to do with a multi-step training approach? Is this something with a new architectural structure? Like the Aurora model uses they have an explicit different vertical sub-embeddings that they use to represent the vertical structure. They do seem to get some improvements in their stratospheric performance as a result. So I think there is something in that direction that needs to be further pursued. I also think the physical consistency piece is important, and making sure we have all the right variables to represent certain processes. There's a question: do we need to explicitly represent things like how much can be needs to be explicitly represented versus what needs to be implicitly or what can be implicitly represented? So the difference being, do you need extra fields that can handle clouds and moisture or vertical velocity or geopotential height even? We don't include that explicitly in our state because IFS doesn't include it specifically in a state. Do you actually need to have another potential option is, do you need to diagnose some of these fields explicitly in your model architecture and back propagate through that? Or can you just predict them as another output of the neural network? A lot of groups are doing the latter, but then if you actually try to look at the consistency between fields, it doesn't show up. However, there have been other studies in the parameterization emulator space that find better stability when you predict a core set of fields and diagnose the rest. This was Yuval and Gorman from a few years ago had a paper on this for like convective parameterizations. So I haven't seen a lot of people try this in the AI NWP space yet. I think it's an interesting open target and something where I'm very interested in trying out and seeing how much does this help, how much does it help. In some cases, it may not be a huge change in accuracy. It may actually make things a little worse because you're getting sharper fields and you're not smoothing things out too much. But if you care about that physically consistent relationship, enforcing it at the and how you diagnose fields could be a key to getting better model performance and potentially better data assimilation in the long run.
All right. Cool. Thank you. Yeah, so it seems that your talk was very clear. There are no questions from the audience. And thank you so much for answering my questions. And thank you for presenting and showing this very nice and super exciting project, the Miles credit. And I'm sure to have a look. And I'm very excited also to see what comes up next. And I would say that we close the webinar. Thank you everybody for joining. Thanks again, David, for presenting and giving us insight in your interesting research. And then I would close the session for today, and I hope to welcome you soon in the next webinar for AI for Good. Goodbye.
Thank you so much, everyone.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event.
Thank you, Alex.
We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.